All right, now that we've had a chance to kind of explore a little bit about putting schedules together, we're going to take a look at a thing called critical path analysis, where we're going to find out what our critical pathways are to be able to finish a task in the least amount of time possible, right? So we're looking at the paths that take the most amount of time so that we can go ahead and make sure we map those out. So one of the things we're looking at here is what's called the order requirement digraph. And it's a method we can use to find the lower bound on how long it will take to complete a job, assuming we've been given a list of the component tasks, how long each task takes to complete, and for each task, a list of prerequisites. So essentially looking at the information that's provided in this table. The order requirement digraph is a directed, weighted graph in which each task is represented by a vertex labeled with the time it takes to complete, and there's an edge directed from that vertex to another one if it is a prerequisite. So let's go ahead and start building this. The first thing I'm going to do is look at the ones that do not have prerequisites, because those are going to be all of my first tasks that I do. So T1, T3, T4, and T5 are all tasks that do not have prerequisites. So let's go ahead and get 4 boxes here. All right, and within those boxes, what I'm going to do is go ahead and label. So T1 goes in there, and then I put a little 4 so I know how long it takes. And then T3, and again, that's a 4. T4, that's 2 hours, and T5, that's 4 hours. Okay, now that all of those are done, I take a look at the ones that have prerequisites. So if I look at T2, it requires that T1 be completed. So from T1, I am going to put together another box. So T2, and this is going to be a 1-hour task. And I have a line going from T1 to T2 because that is a prerequisite. All right, now let's go ahead and take a look at other ones. T6 requires 2, 3, and 4. So T6, let's go ahead and get a thing here. T6 requires 2, 3, and 4. And T6 is 1 hour. And so I'm going to draw 2, 3, and 4. Okay, so 2, 3, and 4. So I've got T6 done. And now I'm going to look at T7 requires T2 and T3. So I'm going to stick that same. Okay, so T7 takes 1 hour, and it has the connection of 2 and 3. So 2 and 3. All right, so T7 is done. T8, it goes T2 and T5. T8. T8. And T8 is 1 hour. And it's T2 and T5. So T2 and T5. So all these are arrows. All right, so T8, T9, T3, T4, and T5. T9 is 2 hours. T3, T4, T5. So T3, T4, and T5. That almost looks like a nearly complete bipartite graph a little bit. All right, so that is my order requirement digraph. Okay, so find a directed path P in your directed weighted graph D, which has the biggest total weight. This path is called a critical path. So let's take a look at what I've got here. So I have 4 hours, then 1 hour, then 1 hour. So that's a total. Oh, I'm not done. I forgot. We forgot T10. T10 has to go at the end here, right? Before we could do our critical path. So T10, and T10 is 2 hours. And that is going to be T6, 7, 8, and 9. So all of them are going to go to T10. Perfect. So we know that T10 is going to be included in all critical paths. So we have one here that's 4, 1, 1, 2. 4, 1, 1, 2. So that's going to be a total of 8. Oops. Hang on here. Let me get this a little bit cleaner. So 8. 8. If I do T1 to T2 to T6 to T10. Okay, so that's 8. If I do T1 to 7, 10, it's the same thing. And then 1 to 8, 10, it's also the same thing. So I have 8 for those as well. T1, T2, T7, T10, and then T1, T2, T8, T10. All right, so all of those are 8. I do not have a 2 to a 9, but what I do have is a 4 to a 9 to a 2, and that is also 8. So T5 to T9 to T10. And then let's take a look if there's any others. This would be 2 to 1, 2, 1, 2, that's 5, so that wouldn't do it. 2, 2, 2, that's 6, that wouldn't do it. So this one's not included in any of those. 4, 2, 2, that still gives me 8. So I guess that's another solution there, right? Would be T3, T9, and then T10. And then let's see if there's anything else that would give us 8. Everything else I see gives me less. I think we got them all, right? Anything else that's below that? So those could be considered all my critical paths. All right, so what does P tell you about how long it will take to make the tractor? Does the number of workers you have available perform the task play a role in your answer? Okay, so to make one tractor, I need 8. Well, I shouldn't really say hours because we don't know that it's hours. Okay, so I need 8 units of time to complete. 8 units of time to complete. That's if I have plenty of workers. Okay, once we start getting down to less than what I need, right? Like in this case, maybe 4 would do it because I could start all of my non-prerequisite tasks from the get-go. All right, we could say a job is ready if all the prerequisite tasks have been completed. The list processing algorithm is a method of completing a job and can be described as follow. The list processing algorithm to find a schedule for the tasks. You place the tasks in some order, And each time you have an idle person, assign the earliest task in the ordering, which one is ready and two has not been to assign to a person. If no tasks meet these requirements, then leave the person idle and move to the next time. All right, this is going to take a little bit of time to go through. I'm going to stop this as part 1, and we're going to continue on with part 2 shortly.